Okay, so we can get started. All right, so we'll get started now. So with every class, we'll start with some announcements. Just to recap what we talked about on Tuesday, all the class materials are on Canvas. And for this class, the way we use Canvas is all the materials are organized around the modules page. And then whatever is not covered on the Canvas modules page, you can find the longer range syllabus for the class on my website. So there you can find what the class is going to look like all the way to the end of the semester. And also you can even preview the slides that were used in previous semesters too. So just some organization. So on the modules page for Canvas, you can already find the recitation information. So we have a full set of course staff now. And so recitations will start next Tuesday. So we got recitations on Tuesdays and Thursdays afternoon. There's the locations, there's the TAs. As the semester kind of progresses, what we oftentimes do sorry about that. Okay, so that works. Switch to HDMI. Oh, okay, well, let's give me one moment to double check what's going on here. Okay, there we go. Good. So we've got recitations, TAs assigned, and then as the semester progresses, oftentimes what we'll do is each of the different recitation sessions might focus on a slightly different topic. We'll announce what each of those focus topics are going to be as the semester goes. And then we'll be working with the TAs to finalize the office hours schedule too. What else is on the Canvas page? As always, try to direct your questions to Piazza when you have them. Piazza is good because not only will your classmates be able to help you out, but also there's the whole set of TAs along with myself who can all answer the questions. And so here's our slides for today. Topic for today is your potentially first foray into using Linux. So let's just start with like a quick show of hands, right? Who's used Linux before? A small subset, right? So smaller fraction. How many of these raised hands are from just recently starting to use iLab? Yeah, a good number, right? So for a lot of you, iLab is going to be the first Linux machine that you use. Have you Now, for the people who didn't raise your hands, why do you think you've never used Linux before? Right, okay, everybody who hasn't used Linux before, raise your hands. Okay, how many of you have an Android phone? So keep your hands raised if you have never used Linux before. Okay, keep your hands raised. If you've used Android before, you can lower your hand. If you've used something like a Roku or like a Apple TV or like, I don't know, a Chromecast, you can also lower your hands. If you've ever used Wi-Fi at home, you can also lower your hands. All right, so in reality, everybody's used Linux before. You just don't know it, right? Let's play a different game. Let's play this game called Identify the Linux Machine. So who wants to point out any Linux machine that exists in this room right now? Yeah, back there. Okay, so cool. So you've got Linux installed directly on your MacBook. That's cool. Who else wants to point out some other Linux machines probably lurking around in this room? The what? The what? The Wi-Fi. Okay, the router probably runs Linux. Right, the Wi-Fi router probably runs Linux. Who wants to try pointing out other Linux machines in this room right now? Yeah, back there again. Okay, so anybody who has an Android phone, that's running a flavor of Linux. So we've probably got already dozens of Linux machines lurking around this room. Anyone want to point out other potential machines in this room that run Linux? Yeah. The speakers? It's possible. I'm not exactly sure how the speaker setup is. That probably runs Linux too, right? So Linux is really everywhere. So pointing out here, right, it shows up in all kinds of form factors. Oh, even forgot, right? A lot of smartwatches. So if you have watch, that's not just an analog dial. Probably somewhere deep in there, it runs Linux. All kinds of sensing devices, Internet of Things devices, so the speaker setup, motion detectors potentially in this room, Raspberry Pi, tiny computers, Roku TV sticks, Android phone OSs. You can run Linux on your laptop. Our server scale departmental computers, the iLab machines, are all Linux machines. Most of the internet, ranging from the routers to the servers, they all run Linux. And then if you have like a Facebook account, your data is stored by a Linux operated file system, right? So we all use Linux. Everybody uses Linux, whether you know it or not. Who wants to tell me about what are the advantages of Linux? All right, so maybe we'll turn it around, right? What does Linux contrast to? So these machines run Linux as opposed to what? Yeah.
Operating system. Usually use it when you use like machines when you want to run like Docker and a lot of like virtual machine related things.
Yeah, so we're familiar with operating systems, right? Linux is an operating system. The operating system operates your computer. It coordinates a lot of the core functions of the computer, so you have different programs going on at once. It schedules those programs to execute. It manages the storage system, so all your files are organized by the operating system. It's also coordinating the network communications for your computer. And Linux is just like Mac OS, just like Windows. It's an operating system. But what's really different about Linux is no particular commercial entity owns it, right? It is a product of thousands, if not millions, of engineers' time, different engineers working together to develop an open source operating system. So it has some advantages, right? Because it's open source, you have a large community of engineers investigating, like, what's happening with the operating system, right? So there's no kind of lurking privacy or security holes that cannot be detected or cannot be researched upon by different people. And also just in general, right, by kind of getting rid of a lot of kind of higher level application utilities, Linux is a really critical piece of all computing, right? So as I said, the internet, data centers, routers, to personal devices, all rely on Linux infrastructure. And so it's critical for you as a practicing computer scientist to use it, right? To be familiar with it and to use it in your practice. Okay, so that's kind of motivation for why this class really transitions to using Linux throughout the coursework. Who here has already activated an account on Rutgers CS iLab? Yeah, good, most of you, right? So if you have not, go ahead and do that today, right? There's no reason to delay. There are a bunch of tutorials on these links here. And today what I'll be doing is I'll be demoing the particular way I set up my programming environment for this class. You don't have to set up yours exactly the same way. The TAs might help you set up some other way, or your classmates might help you set up in a different way. And really, all this is we need several pieces to work together, right? One is we need to control the iLab machine, right? So we want to enter our commands to run programs. The second piece is we need a way to move files around, right? So I have a personal laptop. You know, when I'm ready to submit my homework, I might want to move my homework from iLab to my machine and put it onto Canvas or vice versa. And you need a way to comfortably edit text files, right? So I'll show you kind of my particular setup today and demo some first programming tasks on iLab. Okay, part 2. So straight to the homeworks, right? So the description for the first programming assignment, PA0, as mentioned on Tuesday, is already out. And this really is mostly about getting your environment set up and then solving a kind of number puzzle as kind of the first programming task. So we'll try to walk through kind of this step-by-step for you to get set up here today. And first things first is you need to get the homework files from GitHub, right? So who here has used GitHub before? Somebody want to tell me, like, in what context you've used GitHub? Yeah.
When you have a coding project and you want to share files, and you can use a concept called branches to basically divert from the main, which is like the final version of the code, to work with others.
Okay, that's kind of jumping too many steps further along, right? So you talked about branches and forking. How about just like a more high-level thing, like what is GitHub? Why do we use it in this class? What might be useful for this class? Yeah. Yeah, it's like Google Drive. Yeah, it's a great explanation, right? It's like Google Drive for programmers. This way I can push homework files from my directories up to a shared repository for the class. So just yesterday, I added another example to the repository. So we'll be playing around with this program called rootFinder today. And then as the next assignments, PA1, PA2, PA3 come out, they'll be pushed onto this repository as well. Okay, so how do we get these files to your computer? Yeah. Yeah, so in order to get these files onto your Linux environment, you'll want to clone the repository. So clone just means take a copy of the files in this repository and put them in the same directory structure on your Linux account. So you can copy this URL, this link here. We'll go to iLab now, and in order to log into iLab, you'll want to put in your username, and the machine is going to be ilab@cs.rutgers.edu. Right, so this is just your user account at a machine name. And you hit enter. Nope. You want to use the command, SSH, right? So SSH means secure shell. And what if we want to know a little bit more about what SSH is? Right, so what we could do is just type in SSH. It will give you a very terse printout of what this program is. If this seems kind of gibberish to you, that's because it is. And a more helpful explanation of what this program is, you can always say man, which is short for manual, and say, show me the manual for SSH. Okay. It's having a hard time pulling it up, right? Or you can Google it, right? Just Google SSH, it'll tell you kind of the arguments to SSH. So the plainest way to use SSH, secure shell, is to say your username, as I mentioned, 804, that's your net ID, iLab, cs, rutgers.edu. Okay, so then if you've set up your account, here's where you put in your iLab password, which is probably or potentially going to be distinct from your NetID password. So that's another place to not get hung up on. Okay, good, right? So now what's happened, right? So now we are in a command line, which is different from the command line that I had been using here, right? So up here, I was interacting with just my laptop. Down here now, anything I type here, this is going to the remote computer. This is going to another computer. How do I figure out what's the name of this computer? Right, computers have names, right? You can always ask, tell me what's the name of this computer I'm on. So it says the host that you're on now is called iLab 4. Right? So what's happened here? Something slightly tricky has gone on here. Up here, I said I wanted to connect to iLab@csrutgers.edu. How come down here it's now iLab 4? Anyone want to take a guess? Yeah, back there.
You connected to one of the iLab computers at Rutgers.
Yeah, so short answer is there's actually multiple iLab machines. There's 4 big servers. Each of them are extremely powerful multi-user machines with a terabyte of memory. And they're just named iLab 1, 2, 3, 4. There's also a bunch of other machines too. And when you say iLab, when you say I want just to connect to iLab, it'll assign you to one of the computers that's less occupied. Right? So in this particular case, we're on iLab 4. And we wanted to get our files from GitHub, right? So we'll copy this string. We'll go to somewhere we want to do work, right? So what I've done here, let me just take a step back, right? So here I have my directories. A bunch of these are just kind of directories you have in your home folder. I have a folder called teaching, so I want to go into that directory. I say cd, change directories into teaching, and ls, list the files, shows me what's in here. And on Tuesday, I demonstrated how to create a folder CS211. So just in order to demonstrate again, so let me remove this directory. So say we're working on CS211 right now, right? Let's create a folder called CS211. So make directory creates the directory. We can go in. And now what we want to do is we want to copy this whole repository for this class wholesale into here. We'll do git clone and clone that link that we had from online, right? So here's the name of the repository. We can look around now, and there you go. We have now our 2024-211 directory. And in here, we have the files for PA0. So this is just a quick summary of getting those files, getting the programming environment, and then just kind of looking farther ahead, right? So this directory, 2024, 2021, this down the line will have the programming files for all of the programming assignments. The first couple ones, just kind of as recap, are relatively lower weight, and these are about getting you to be familiar with programming in C. Okay, anything I can clarify up to this point, just getting the files? There's a hand raised back there. So logging in, it would be SSH, your NetID. So first you have to set up your account, right? So let's keep these kind of detailed debugging questions to either after or during office hours or during recitation, right? We can't work through kind of one-off debugging what's going on your login or your program in class. Okay, so next part, right? What's everybody's native programming language so far? Right, what are we most familiar with as programming languages? Go. Java, okay. Anybody have any other experience outside of Java for the classes we've taken so far? What's another popular language? TypeScript, okay, I'm not actually sure what that language is. All right, go ahead. Yeah, Python, so that's another really common language that we use to do a lot of projects in programming assignments, yeah? SQL, right? So if you've done database work for some project, you might have encountered SQL. So for many of us, C is going to be a new language to encounter, right? And on Tuesday's class, we've kind of mentioned some of the motivations for studying C. It's an important language to do systems work. And because it's been around for a long time, learning C and knowing how C works lays a good foundation for learning a lot of languages that descended from C, right? So C is kind of this big mother language from a long time ago, which continues to have an impact on programming today. And so what we'll do, right, as kind of our philosophy for learning C is, okay, you know, there's a hierarchy of really understanding how to do work, right? So we could take all day and just try to read the specification from a book, like Modern C. Or we could kind of like read it from our digested material, like these course slides, or from some of the notes posted on Canvas. You could just sit here and watch me program all day and try to somehow absorb learning how to program that way. But the main way in which we'll practice, right, is to really get hands-on programming experience, right? So this is like the med school philosophy, right? You got to see one, do one, teach one, right? So we'll practice today. Good. So what we'll do now is exactly that, right? We'll jump into looking at some examples and see what makes it work, right? So this first program that we're going to interact with is going to be already shared in the PA0 directory. This is in the folder called rootFinder. And what rootFinder tries to do is it will tell you if a number is a square, right? So if you give it 4, it will say 4 square root is 2, and 2 is an integer, so it's a square number, right? If you give it 9, it'll tell you its square root is 3. But if you give it a number like 5, it should find that 5 is not a square number, so it should tell you that it's not a square number. So let's take a look at the source code for rootFinder. Find a program that says whether or not its square roots is an integer. And we'll start by the first piece of the program, the headers. So what I'll do now is we need several ways to take a look at this source code. Right? So here's the source code rootfinder.c, and we want to take a look at it. So there's several options that we can try here, right? If we wanted to just only peek at the code and not edit it, my recommendation is to use less. So less is a program which just looks at a file, read only. So less rootfinder.c. So there it is, right? This is the source code. Other options, if you need to edit this source code, there's a couple big options that you can use natively on the terminal command line. One is Vim. Right? So Vim is yet another popular text editing tool for modifying files on a Linux machine. And the other big one is Emacs, yet another text editing tool. Right? Same, you have an environment for editing files. Yeah?
Is it possible to lower down the lights to the front? It's kind of hard to see the darker text.
Sure thing. And you can tell that I'm not an Emacs user because even I'm confused how to get out of this environment. Better? Yeah, that should be good. OK, how do I get out Emacs? Anybody know the key combination to get out Emacs off the top of their heads? Who was that? Yeah. Control Q? Nope, it's not letting me get out. All right, let me just reboot this terminal. Another way you can get around and edit files is you can access your remote file system via a utility like a SFTP, secure file transfer utility, such as CyberDuck. Right? So what this does is you can enter in your login information for the remote machine. It will connect you to a session on the remote machine, and then you can look at your file directory tree via GUI like this. And you can see that there's correspondence between what the GUI shows for your file directory and also on your terminal here. Right? Who's used something like VS Code before? A huge majority, right? So most of you are very accustomed to use something like VS Code. Right, what are kind of the big UI components of like VS Code, right? These things that I've shown you so far, do they exist in VS Code? Yeah. Yeah, so the VS Code UI is set up basically to have exactly all these things, right? You've got your terminal to run your commands. You've got your file explorer, which is really just down underneath the VS Code implementation, is just running a FTP transfer protocol. And then it has a text editor built in right there as well, right? So really, this is exactly the same setup as something like VS Code, where you're looking at different views of your programming environment. Okay, right, so I use CyberDuck to connect. And here you have this option of just setting a text editor, which opens up your file for editing. Okay, so now finally we have a view into rootFinder.c. And following through our outline here, our next step is to take a look at the headers. And here it's saying I want to include several components into this program. One is called standard library. Another is standard input-output. And a final one is math.h. Right, so these are really just files that exist on the Linux machine already installed as kind of the C language implementation. And here it's saying pull in these headers. What is this kind of like in Java? Is this akin to, this remind you of something in Java? Yeah. Yeah, so in Java, we have a similar idea, right? In Java, you can import libraries from the Java library, standard library, for example, or Java collections library. And you can see that C's approach to have these includes eventually kind of in its descendant languages, such as Java, became this feature where you can import packages, right? So this is already kind of a little example of a way in which C is influential on descendant languages. The next piece, what we'll do is to now get our program arguments into the C program, right? Let me like orient us here, right? What is this like? In Java, where do the command line arguments go? Yeah, hand back there.
Do they go into the arguments array that's already built in?
Good. What are the magic keywords in Java that we all learned? Right? I hear it, yeah. Public, static, void, main, string args, right? Okay, in Java, you have this thing called string args, right? If you don't remember what that is, maybe go do a quick review. So in Java, you have this variable called args, which is of type, what's the type of args? Of string. Yeah. It's an array of strings, right? It's not just one arg. You have multiple different arguments. So same thing, right? Java descended from C, and here is where all that originally came from. The arguments to the C program come in as a command, as a argument called argv. Right, so let me back out a little bit. Let's go to the source code. So here we are, our C program, and we've got our main function, just like in Java, right? Our main method, our main function. Main returns a type integer, and main as a function takes two arguments, right? So this already is a little bit different from Java. Here we have two components to the arguments. One is called argc, which is an integer. And we have a second argument, second parameter, which is an array of character pointers, right? So what's going on here, right? So this is going to be our first little foray or kind of exploration into how you get strings in a language, right? So what this is going to be is in your argv array, it is an array of multiple strings, right? So what's a string, right? A string is really itself just a sequence of characters ending with a null character, right? Ending with just the number 0. So in the C language, all of these things are really all the same. You've got strings, you've got character pointers, and character arrays, right? So let's see if we have a concrete example here. So we've got, let's play with this example via this component here, where we'll take a look at the arg array. And this line here, what it's saying is take the first argument of argv, right? So argv refers to this argument here, this parameter here, and it says it's expecting to find something in the first element of the array. Okay, so why 1? Right, let's put this side by side here. There should be something slightly interesting here, which is how come we want to read the first element of the array? Should we try experimenting? So let's experiment and take a look at what argv element 0 is going to be. Right? So I've got this program here, and we want to first interrogate what does this thing mean, argv item 1. Right? And so I've printed this out here. Let's take a look at what is argv item 1. Right, we'll run this program. It's possible. Yeah, so it says, OK, I execute the program, and the first argument, item 1, is this printout here, and it says test, right? And as one of your classmates point out, it's running into this next line here exactly because for better readability, it will be good for me to put a new line there. And there you go, right? There you have test, right? So that's a little curious. It calls this item 1. Anybody want to take a guess on what item 0 is? Yeah. The pointer to that? Not quite. Another guess? the text that we use to run the program, in this case, a.out, right? That's a good guess. Let's experiment, right? Let's take a peek at what argv item 0 is. Compile and run, and there, right? It says a.out, right? So really, this whole program, just in the inputs here, something curious has happened, right? The 0th element of the argv array of strings is the name of the program, and the subsequent arguments are going to be in items 1, 2, 3, 4, and so on. Right? So in this case, this program that we want, right? This slide just basically says the same thing to that effect. The first item of the argv array is a.out. And what is a.out? It really is a sequence of characters ending with the special character, which is just 0, terminating that string, right? So the subsequent arguments are in the later elements of the array. Anything I can kind of say here just to clarify what what we covered so far? And really, we're studying the very first line of this program, right? Just to kind of really understand what's happening inside. Yeah.
Why is it argv instead of args?
Sure, right? So why argv as opposed to args? Right? You want to take a guess?
V stands for something I don't know.
So in Java, famous words, right? Public static void main string args. Does it really have to be called args? Some tentative head shakes? Yeah, you can name it whatever, right? That's really just a naming for the variable in the function signature, right? So just like in Java, you don't really have to call it args secretly. We can call it args here too, right? So we want to replace all instances of argv, and this will be perfectly fine, right? It compiles, it recognizes that really this is just the name of the variable for this function signature. Yeah?
Is there a reason why we use asterisks and square brackets?
Is there a reason why we use asterisks and square brackets? That's a great question, and that's all about pointers, and we'll get to pointers next week, right? So let's just kind of learn our ropes with what we would do in Java first in C, and then we'll really dive into what's strange about C. Yeah? Yeah, so what is this character here, right? This ends the string, right? It's just a special character which terminates this string. Yeah, and this previews this mystery kind of previews farther down in the class, right? But one of the themes of this class is really just all data is also just numbers. So each of these things are just numbers, and this is yet another special number that just says this ends the string here, right? We'll take a look at how all of this is stored in memory as a theme of this class. Yeah? Sorry, I couldn't hear that. Ah, good. Where was test set at args1? Right? So here it says args1 printed out was test. So where did that test come from? All right, where did this test come from? It was our command line argument, right? So the name of the program is just called a.out. And instead of saying test, suppose I want to say my argument. There. Now the argument is called my argument. Anything else I can clarify here? Yeah.
What is the /a.out?
Good question. What is this a.out thing? We'll get to that. Anything else? Okay, so that's a lot of things that we can say even just on the first line of code. But that's what we want to do, right? We want to really study how the language works and why it's structured that way. Next thing, right? What we want to do is we want to now open a file, right? So let me take a moment to explain the setup of this program here, right? So in this directory, we'll want to run the program rootC, which compiled into this program called a.out. And we want to give it as input various test cases, right? So in these directories, there's a file called test0.txt, which stores a number, storing another number, right? So the goal of this program is to open this text file, read this number 30, and say 30 has no integer square root. Let's see what other test cases. Right, test 2 reads 36. It should tell us that 36 square root is 6, which is an integer. Right, so we want to have our program open these text files. So how do we get our program to read a text file? And again, right, let's connect this to what we would have done in Java. How would we have done this in Java if we wanted to give our Java program a text input? Okay, there's a pipe concept in Java. Anything else? Yeah.
You could either pull it straight from args or use scanner class.
Okay, good, right? So scanner class, right? So how would we have used the scanner class in Java? Or do we already forget everything about Java over the winter break? Yeah. Instantiate the scanner class, and what other arguments do we give to the scanner class? Yeah. Yeah, you got to give it the file name, right? So scanner will take, in the correct setup of however you would have done it in Java, it would open a file name. And so what we're trying to do here is exactly the same thing. We want to open a file name. The example code that we have here is kind of the guts of how something like scanner really was doing underneath, right? We want to open a file. We're going to give as an argument to open the file name. And we're going to do this in this additional argument here called R. And this simply says we're going to open this file in read mode. Right? Other arguments, you could give it the character W or the character A, and this opens it in different modes, right? Writing mode, append mode, and so forth. So right now we're just opening the file that says, say, 36, and reading from it. Okay, what else do we see on this line of code here? Right? What is this type here? Anybody want to take a guess? I'll take an answer from back there. Okay, so that's a good guess. So we've got a pointer, so we'll get to how pointers work. So just preview of next week, we'll understand what this thing is, what this character means starting next week. But it's a pointer, but what's this capital file? Where is this coming from? Yeah. It's a data type, right? So this is not some super special keyword in C language. This is a data type which is defined in this header here, right? So the standard input-output library says there's a data type called file. You're creating now a variable name called FP, which is a pointer to the file data type, right? And FP, again, is just some name that we give it here. It just means file pointer, right? So this can change to be whatever you want it to be. Capital file, this is a data type defined in standard I/O.
right? And so the next lines of code, what are we doing next, right? So the next couple lines of code, this is really just elegant handling of a mistake, right? In Java, what would be a similar equivalent to something like this? Yeah. Yeah, so this is really just a little primitive approach that we've implemented here, which is a lot like try-catch exception in Java, right? We're handling a situation where suppose we give it a faulty argument, right? So let's give it a test case right now. We'll compile the program. We'll run our program with this strange argument called myArgument. And it says, OK, it tried to open a file called myArgument. That's not a valid file name. And so it entered this block here saying fopen failed and return. OK, let's study this here now, right? Isn't this kind of peculiar? What does it mean to return a value here? What's it returning out of? Yeah. Okay, close, not quite. Yeah.
So this main method returns integers, so exit underscore failure is an integer that's defined within like more standard language.
Good, right? So let me just basically say that again, right? So this return, what's it returning out of, right? What's the function that we're returning from? Well, it's the whole main function, right? We're returning out of the whole program itself. And what type should it return? It should return integer. So a guess on what this thing is. This is just some number, which is, again, defined in our header somewhere, probably standard library, right? This is a standard number called exit failure, and just indicates that this program did not succeed. What's the equivalent of this in Java, right? This is also a little strange. Why does main return integer here? What will we have done in Java instead? Yeah. Good. Let me turn that around, right? I think I'm saying stuff that's more confusing at this point, but famous words of Java, right? Public, static, void, main, right? So what does it mean that Java's main method returns void? Yeah. Yeah, two voices, yeah. So both are correct, right? Java's main function, main method, if you say it returns void, void just means it doesn't return anything. Could it be something else? Could Java's main method return something? Go check the documentation, yeah. Sorry? It could, yeah. Java's main method can return a type, right? It can return integer. You can check the Java specification. And again, that descended from C. In C's main method, we expect it to return integer, which just indicates success or failure. Did this program succeed? Great, 10 lines of code in, and we've talked about lots of stuff so far. Anything I can clarify here before we keep going? OK, so far we've been trying to open a file, right? And this one did not succeed. How do we get it to succeed? We want to actually open the file. What should I do instead? Maybe, yeah.
Your argument in the command line would have to be the directory of the file.
Yeah, so let's take a look at our directory, right? So what should I say instead? A.out is our program. We want to point it to the directory of the files. So there you go. Tests is where our test cases are stored. And the first test case is called test0.txt. And now it should open the file and keep going, right? So now it has a valid path. It did not say failed, and we've moved on, right? We're now in the next phase here. Okay, so good. In our file, test case 0, it has just this text called 1, right? In Java, if we've opened this file, how will we get this number out? What would we have done in Java? Yeah.
Would we have to read it line by line and then it grabs like the first valid term of the first valid term of that instance, right?
Yeah, so in Java, you would, let's say a little bit more, right? So in Java, the typical approach we learned was to use a scanner, right? So what would you do with scanner? Yeah.
You use the method readLine.
Readline, good. So you can say scanner.readline. It'll give you this line. What's the type of that line? Char? Is line a char? Yeah. Huh? Is it already an integer? So I heard some murmurs, right? I believe it should return you a string. Good. So we've got a string, right? But a string's not a number, right? I got this text file, it says 1. But how do I actually get like the number 1 from it? Yeah, so you could do something like integer.parseInt, right? Integer.parseInt takes a string argument and says, I believe this string is an integer. Can you tell me what that integer is? So we've got to do all those stuff now in a C program, right? All the tricky steps it takes to get this text to become a number. So let's preview what's the various options here are. Right, so in C, you've got all these different primitives to read all these components. And you could do this many, many, many different ways, right? So here's just a short list of various options. You could get a character, fgetC. You could get a fgetString, so read a whole string from the file stream. Or you could scan through the string looking for format, right? So let's just see this in action in the code here. Here we're going to use the fgetS primitive. So this is saying that from the file, let's get a string. What are its arguments? So fgetS has 3 arguments, right? First, you got to have the string, give it a number, and then a pointer to your file, right? So let's match this up into the code. I'm reading from the file, good. We put in the file pointer. We read in some number. What do you think this means? Why 256? Yeah. So this is just a number that says we're reading from a file, right? And here it's saying, how much stuff do you want to read, right? And so this is simply saying, read as far as 256 characters in, right? And where does those 256 characters go? Well, it's going to be put into an array of characters here, which we set to be 256 characters long, right? This is simply kind of the lower level implementation of C, where all of this has to be done kind of very clearly. We say, here's a buffer for 256 characters, go to the file, read into the buffer, and you could read as far as 256 characters. And kind of as a side effect, your character is going to be read into this string type here. Okay, so let's see some of this stuff in action, right? All these things that I claim, let's play with this a little bit. First things first, let's stop the program there. And these things that I claim, right? So let's see the outcome that we expect. Right, so this is saying that good, right? At the end of this program here, it says it's read in 1 as a string. One of the things I claimed is this says how many characters to read, right? So what do you think will happen if I set this to 0? Yeah. It's not going to go anywhere, so let's give it a try. Segmentation fault, right? So this says that we've read in no characters, and so an attempt to print the string, there's no string to print there, right? So segmentation fault. Any guess on what happens if I suppose I try to read much bigger than the buffer offers? Let's give it a try, right? Oh, even better, right? So the compiler says we're doing something silly. We're trying to read 512 bytes into a buffer of size 256, right? So the compiler said, don't do that, right? And it prints that out while we're trying to compile it. Some more details that we can take a look here. Shall we inspect what buff is? Right, so let's take a look at, after reading, what's actually inside this buff type, this buffer character array. Right, it's also 1. So let's take a look at this kind of in further detail, right? So buffer, what does buffer contain at this point? Anybody want to take a guess? Yeah. Okay, so the guess is that it's got the character 1 followed by nulls, right? So let's give that a try, right? What we'll do now is we're going to print out the components of buff as an array, right? So let's scan through this kind of manually. Let's look at what's the first thing in buff, and then what's the second thing in buff, and so forth. Okay, so the first element that we printed out seems like good. It's 1. Let's inspect it as yet something else. I changed this type here from C, printing as a character, to now D as an integer. So now I'm saying, okay, I've got this array, buff, right? And please print out that first thing in the array as an integer. And now it says 49. So where did this 49 come from? Right, okay, maybe I'm going through this a little quickly, right? So who wants to paraphrase kind of what's happening here? Like what's the weird thing that I'm doing now? Yeah, I'll give you a shot. Yeah. No, sorry, it's this student here. I know I'm kind of like pointing in this general direction, but I want him to go. Yeah, sorry.
So like you changed the letter like from C to D. So now it's like
all this is good, right? So here, originally, when it was C, I was saying, okay, print out that component, this data as a character, right? Indeed, that's exactly what it did, right? So it prints out 1. And now I'm saying, like, please print it out as an integer. It says, as an integer, it's 49, right? So this is hinting at underneath what's going on is this character 1 is itself a number, but that number is not necessarily 1, right? The character 1 is actually encoded as the integer 49, right? So this is previewing kind of like how all data in computers is just numbers, right, later on in this course. Shall we try printing out what the second component of buff is at array index 1? Who wants to take a guess what it will do now? Yeah. It will print out nothing. So let's do a couple things, right? Let's first print it out as character right now. What's this going to do? Let's take a look. Nothing, right? It printed out nothing onto the line. It just gave you the new line, and that line has nothing in it. Who wants to take a guess what I'm going to do? Well, who wants to take a guess what will happen now that we print it out instead as D? Yeah. There you go, right? It will be 0. So let's confirm that. And we'll wrap this kind of a couple slides back to see this in action. Now it's printing out as a number, it's 0. So what's going on here? What's like the point? Why did it put a 0 there? Yeah.
To show that it was the end of the file, or the end of the array.
So it's pointing out that it's the end of the string, right? And this is, we've seen this just now. Here you go. Here are strings in C. What we've interrogated is I've got a string. The string is 1 as a character, but it's a string, right? So at the end of that 1, there is a null character, which is represented as /0, which itself is integer 0, right? We've just peeked into this file, text file of string of numbers and see this in action. Yeah.
So this 0 character, is that like the 256th character, or is that like one after?
So this 0 character is, what's happening here is in this buffer, right? I've got this buffer here as kind of an illustration. I've got an array of elements here, and this buffer is in total 256 long, right? It's an array of 256 items. The first character was 1. The character 1. The second character in the array is /0 as a character. An equivalent view to all of this, all data is just numbers, so this character 1 was really encoded as the integer 49. This termination character /0 was encoded as the integer 0. Right? These two views, up and top and bottom, are the same. And this is what we've just interrogated. Yeah, back there.
So going back to that first line, you have the character 1 and the /0, but the /0 is the second spot. So everything after the second spot is not /0, right? That's only distinct to the spot right next to the end of the string, right?
Good question. I actually don't know. I can't predict, right? So your question is, we've interrogated array index 0 and array index 1. And a good question, as you said, is what's next, right? And actually, I'm not sure either, but we can give it a try, right? So let's just go ahead and do that. Let's interrogate what is the element at array index 2, the third item in the array. as first a string, as first a character? Nothing. And then maybe as a integer? 0, right? So what it's done is for the rest of this buffer that was empty, it's continued to fill it in like so. Like that. Good. So far, we are 15 lines in, and finally we're about ready to get our integer from the string, right? So what we'll do next is we'll use a special function in C called a to I, which says take a string, convert it into integer, and now store that as this variable, integer variable called square. The next line of code, perform a square root. So where is this coming from? Right, or even better yet, where did all of this come from? Where did fgets get from? Yeah, so fget_s, this was a IO input-output function defined in standard library IO. A to I, take a string, turn it integer. This is provided by the standard library. And this function here, please take the square root of a number. That was provided in math.h, right? And you can look for kind of the definitions for all of this. C math library will give you a full list of all these functions that are available in each of these libraries. And what we've invoked just now is square root. Right, there you go, square root. Okay, so finally, right, we now have actually gotten the number into our program. And let's actually do some work with the number, right? And so all of the control flow statements that we're used to from Java basically carry over. You can write if statements just as before. You can write for loops, while loops, do while loops, all just as before. The tricky kind of control flow statements, break and continue, carry over just as before. Maybe pause here, right? Have we used break before in Java? Some nods. Yeah, so what does break do? What is the semantic meaning of the break statement? Yeah. Break breaks out of the innermost loop. Yeah, right, so for whatever innermost loop that you're in, break will stop the loop and exit from the loop. What does continue do? Yeah. So continue skips the current iteration, so it won't finish this current loop, but come back to the top of the loop body, right? So we'll see how this is implemented in the C language in this class. Same thing, another theme, right? C language is old. These statements influenced Java. Okay, and so here's another kind of just tutorial slide. We've already encountered a lot of this just now. So implied, I was doing this before. In Java, how does Java print stuff? Yeah. System.out.print or print line, you've got both options. How does Java figure out what data types things are? Yeah.
You have to assign them so that when you reference them in the future, it already knows what type it is.
Okay, that's a potential. Okay, so let me phrase it this way, right? Java's system.out.print. Now you have a parentheses. What can you put in that parentheses? What can you give to print? A string, good. What else? Does it have to be a string?
Like, can you pass in any object and it'll use the toString implementation?
Good, right? So that's the key answer, right? You could give Java's system.out.print whatever you want, right? It could be an object, it could be an integer, it could be a double, a floating point. And what Java will do is it will always turn whatever you give and invoke the toString required method of that function, right? So all objects should have a toString function. In Java, in C, things are a little bit more primitive, right? So in C, everything that you want to print, you have to tell it, well, what's the type, right? So the format of this, let's just give it some practice, right? This task that we've been doing just now, where we've been playing around with printing the components of this. Well, we could have done this like this, right? So this is saying I want to print out a string. It's going to be expected in this format. And I can annotate this, right? I can say buff0 as a character is going to be character, and say new line, buff0 as a integer is going to be as integer, new line, right? So this is going to pretty print everything exactly as I specified. So here it's saying it's expecting I wanted to give it first a argument here, C character, and we need to tell it twice, right? So the first one goes to the C print type, and the second one goes to the integer print type, interrogating what buff item 0 is going to be as a character, as an integer. Let's compile and run. There you go. Right, exactly as I wanted to print it as character, it is a 1. That 1 is really encoded as the number 49. Good, right? So, and you can look at the comprehensive documentation of all the ways you can print here at this link. And let me just kind of say one final statement, right, about, so what was this program that we were doing, right? In Java, if we had source code, what do you do to run the Java program? Right, let's take 3 minutes to discuss how this program actually comes to be. Yeah. Good. So can somebody tell me what Java C is? Yeah. Okay, so Java C is a compiler, and compiling what for what? Right, so in Java, you have your Java source file. Java C compiles the .java source file into your class file, and then you can say Java invoke that class file, right? So here, this is exactly the same thing. We use a different compiler now. This is the GCC C compiler. And what I've been doing is GCC, the C source file, -lm, right? So what this is saying is I invoked the math library in our program, and so please give me a link to the math library, right? So this gave us a.out, right? So what if we want to change the name of that program? All right. Does it always have to be a.out? No, right? So we could say instead of dumping it directly as just a program called a.out, you could say, please give me a better name as the output. Call it rootFinder program. And there you go, right? Now the program name is called rootFinder program, right? So a few other things that we'll set as standard in this class, recommended flags to give to the GCC compiler. Enable these flags to give you nice compiler warnings. And also these flags to check how your program is using memory, right? And then finally, as kind of the infrastructure for this class, what you can do to test all the programs in this class is you can invoke the autograder. And this will run the autograder, right? And the autograder right now, what it's done is it's run the program, and it saw that, well, I'm right now printing out this strange output, and so that's not the correct answer. And it's saying that's not the right answer, right? So if we revert the program to its original state, run the autograder again. So this will run through all the test cases, and this is the expected output for rootFinder, right? So that's a summary of basically the rootFinder program, and we'll come back on Tuesday to work more on PA0.